Okay, morning everyone. Today we're going to continue our discussion about the asymptotics of order statistics. This is what we did at the end of our last lecture. So we define order statistics by sorting n random variables from the smallest to the largest. And please bear in your mind that even though in our writing we didn't include n, but n should be there. So we have to first fix an n before we can sort the n random variables. So here, this notation we use in common is just a short way of writing the order. But please bear in mind that we have the total n here. So we started by talking about the extreme order statistics. By extreme, we mean the largest or the smallest. And here, the general idea for us is to find an and bn such that an times xn, the largest, minus bn, the difference, it will converge in log to some random variable, and the random variable follows some non-degenerative distribution. That means that the limiting distribution is not a constant. So we give an example for this x1 to xn uniformly i.i.d, uniform between 0 and 1, and we're interested in the maximum. Okay, and we did this derivation. We basically just follow the definition of CDF, right? So if the maximum is less or equal than something, then it means each one in the sequence must be less or equal than the same t. And then by i.i.d, we can write it as the product. And because of i.i.d, we can write it as the probability that x1 is less or equal than t raised to the power n. And then we can get the limit. So essentially, why do we want to talk about uniform distribution? You will see very soon. The reason is that if you're familiar with the generation of random variables from any given distribution with a given CDF function, then you know that in the computer, what it is doing is that it samples from a uniform distribution, and then it supplies every drawn values with the inverse of that CDF function. Then you can convert the drawn sample to be coming from that given distribution. So we'll see that later. But this is the reason why if we can deal with this uniform distribution, it becomes a lot easier. The reason is that if we change the distribution, the order will be kept. The smallest is still the smallest, the largest still the largest. The only thing we change is their values. Okay, so the important result from last lecture is that we found that by setting an equals to n, bn equals to 1. So we did here. We found that the limiting distribution of n times xn minus 1 right here. The CDF of that is convergent to exponential t, and t is being negative. So then we did another inverse, right? By changing the sign on both sides. So basically we can find that, okay, n times 1 minus xn is convergent in law to exponential distribution with parameter equal to 1. So this is a very nice result. So what does this mean intuitively? It's saying that given you have n random variables, i.i.d, drawn from the interval from 0 to 1. So let me just draw the understanding here. Suppose that this is 0 to 1. And you randomly draw n random variables from it, right? So then, you know, after you do the sorting, this will be x1, this will be xn. And what you also know is that, so from our discussion here, okay, you can see that we do have our largest xm converging in law to 1. So you know, the more you draw, the two boundaries are going to be pushed to the two ends. So x1, the minimum is going to converge to 0. Xn is going to converge to 1, right? But how fast does that converge? Here we know if we know this thing, okay? So this is shrinking. Let me get another pen. So we know this part is shrinking to 0, right? But what we can do is that if we multiply this part by an increasing constant m, then it's not shrinking to 0, but it's convergent to a distribution. And that distribution is exponential one distribution. So if you're familiar with exponential distribution, you know that it's defined on the positive part of our real line, right? It's defined from 0 to positive infinity. And it has like a shape where you have a mode somewhere and then it goes down. That's the density function shape. So basically, this will tell us very interestingly that if we multiply the shrinking part by m, then this part is behaving like an exponential one random variable, more and more like that as your n goes to infinity. And similarly, we can say the same thing about this side. So even though we didn't prove it, but you can use your intuition to see here we do have some symmetry. This left end should behave similar to the right end. Okay, so that's example 1. And we're going to give you another example also about the maximum. This is a very, very important result, and it's related to another distribution that has a name. Okay, so now we change our condition from x1 to xn, i.i.d. uniform 0 to 1 to now they are i.i.d. exponential 1. Okay, then the question is the same. What is the asymptotic distribution of the maximum? Still the same question. And similar to our example 1, we want to derive the asymptotic distribution of am times xn minus bm. And for simplicity, we just set an to be positive. So we don't need to worry about the signs in any inequalities. And here we again start with defining the CDF of this quantity. We define it as the probability am times the maximum minus bm less or equal than t. Okay, because of am being positive, we can write it as the probability xn less or equal than t over am plus bm. Okay, again by i.i.d, right? We can write this as the probability of x1 less or equal than t over am plus bm raised to the power m. But this happens with some condition. So we know that this x1 to xn are exponential one. So they must be positive. And here, if we write it this way, you see, for x1 is exponential one. So this quantity actually holds if what? So I should say next line. So this value is equal to what? It's actually, we know, let me write it here. So we know that, so given x1 follows exponential 1, right? So we know that the probability of x1 less or equal than t would be equal to 1 minus exponential negative t if t is greater or equal than 0. Let's just put it greater than 0. And otherwise, it's just 0. Because when t is 0, it's also 0. So we combine it with otherwise. So this is the fact we know about exponential distribution, exponential 1. Then coming back here, we just use this argument. We would have this equal to 1 minus exponential to the negative t over am plus bm to the power n. If t over am plus bn is positive, I think this should be negative, sorry, this one. Otherwise, it is 0. Okay, we already obtained the CDF of the distribution of AN times xn minus Bn. Now the remaining question is, what are the values of AN and Bn so we can make this limit of some well-known distribution? So let's play with this term. Okay, let's play with this term first. So you know that ultimately, from our last lecture, we want to have some form like this. So we can have it converge to a limit that does not depend on n. N is going away. And that's our goal. All right. So looking at this term, 1 minus exponential to the power t over an minus bn to the power n. Okay, that's the term we want to work with, and we want to find a limit for it, letting n go to 0. And inside the braces, we can actually write as 1 minus exponential to the power t over an divided by exponential bn. Okay, that's it. And then looking at this term, do we see that we are already getting closer to it, right? Here in this standard form, 1 plus c over n to the power n. And here we have this. So you see, one thing that could be interesting is if we set bn to be log n, then the denominator would become n. Okay, so you see that if we set bn to be log n, what happens is that it becomes 1 over n to the power n. We have that. And for the numerator, we wanted to converge to some constant, and that does not depend on n. So the simplest way to do it is we could just set an to 1. Then the numerator becomes exponential to the negative t. And we have it. So you see, by doing that, then based on this fact, this thing right here, we can actually say, okay, this is converging to exponential to the power negative exponential negative t. That's it. So we can get in a limit like this. And now let's revisit the condition. So we require t over an plus bn to be positive, right? And now with an equal to 1, that's what we said, bn equal to log n. This becomes t plus log n to be positive. And now you see, this would for sure hold for n being large enough. Because here the argument is that t is a constant. It can be positive, it can be negative, but it's prefixed. And then we want to talk about the asymptotics by having n go to infinity when t is fixed. So we can always find such an n to have this hold when n is large enough, right? This holds when n is large enough. So we're good. So then we have the limit for the CDF of an times xn minus bn. Then what's left is what this limit is. So we can give this a name. So the name of this is called a Gumbo distribution. Maybe some of you have heard of it. It's called a Gumbo distribution. Or another name of it is called extreme value distribution. So what does this mean is that if we have T follows Gumbo distribution, okay, then the CDF of this T is actually equal to exponential to negative exponential to negative T. That's the CDF. Then that's how we define the Gumbo distribution to be. And then here we have seen why it's called extreme value distribution, because the maximum of i.i.d exponential, x1 to xn here, what we have is we showed that the maximum of i.i.d exponential 1 minus log n is converging in law to this Gumbo distribution. And this is a very interesting conclusion as well. So we know that it's because the exponential one domain is unbounded, right? It can go from 0 to positive infinity. Then no wonder that once you increase n, the maximum will go to infinity, right? The maximum is getting larger and larger. But we actually found that if you just control that growth in its magnitude by minus log n, then interestingly, this difference is converging to a distribution that does not depend on n, and that's the Gumbo distribution. So this is a very interesting fact. And I think this example is to let us get familiar with, again, about this derivation of the CDF. We didn't do anything fancy. We're just getting the CDF function of an times xn minus bn. And then we find the limit for the CDF. So here, the trick is that we want to find a proper set of an and bn such that the limit is convergent to some limit that does not depend on n. And then we define a distribution for the limit here. Then that's Gumbo distribution. Okay, that's example 2. And now we're going to do another example, which we call example 3.
Excuse me, Professor?
Yeah.
So the regularizer term an is just constant. Does that say something about like the variance of this extreme order statistic? Does that mean that the variance of it doesn't go to 0 or something? Like, is there some easy interpretation?
Yeah, the variance of it doesn't go to 0. You're exactly right. Yeah, because if you see that, yeah, it's actually here. Because if you see that, if you take the variance on the left-hand side, then this minus log n will not get into play, right? So just a shift. But the variance, so basically we're actually saying the variance of this is convergent to the variance of the Gumbo distribution.
Okay, cool.
Yeah.
Yeah, okay, thank you.
Yeah, that's a very cool thing, I think. Yeah, that's right. Okay, now let's move on to example 3. It's again, we're back to the uniform setting. Okay, here we are going to give you some interesting statistic that depends on 2 extreme order statistics. So we define x1 to xn i.i.d from uniform 0 to 1, the standard setting. And we define this what we call the range, Rn to be the maximum minus the minimum. So we're interested in the range covered by this x1 to xn sequence. And then the question is, what is the asymptotic distribution of the range? The range itself is a statistic. Okay, to answer that question, we want to use the result of example 1. So if you take a look at this one, so I was saying that this part and this part, they are symmetric. So we would guess that, okay, they have the same distribution. And that's actually very important for here because based on the definition of Rn, it's depending on Rn, the maximum, and xn, the maximum, and x1, the minimum. So we want to derive the joint asymptotic distribution of x1 and xn. Then we can just obtain this, right? So that's the whole idea. So we want to derive the joint distribution of the minimum and maximum first before we talk about the asymptotic distribution of the range, which is their difference. Okay, so here's how we're gonna do it. So we first want to derive the joint asymptotic distribution of x1, xm. And because here we know the symmetry, right? The symmetry between x1, okay, coming back here, between x1 minus 0 and 1 minus xm. So we're going to utilize that. And also from here, we know if we multiply 1 minus xm by m, the asymptotic distribution is nice. So based on this example 1, we actually interested in this distribution, n times the minimum and n times 1 minus the maximum. Because we know marginally, each of them is converging to exponential 1. So now, how about their joint distribution? So for their joint distribution, we actually can get their joint CDF. Okay, so for the joint CDF, it's defined as the probability of n x1 less or equal than x and n times 1 minus xm less or equal than y. This is what we call a joint CDF for two-dimensional distribution. But this is not easy to work with. The reason is that if we say the minimum is less or equal than something, we don't know what to say about x1 to xn. But if we say the minimum is greater than something, then we can say all the n random variables are greater than that thing. That's easier to work with. And similarly for maximum, it's not easy to talk about the maximum being greater than something, but it's easy to talk about maximum being less or equal than something. So that's why we want to work with, we look at the probability of n x1 larger than x and n y minus xm larger than y. So we work with this instead of that, just because of the reason I said. Okay, and what does this imply? This is actually very interesting. So if we look at this, so it's saying what? This is actually equal to the probability that x1 is larger than x over n. Okay, and of course, x1 is less or equal than the maximum by definition. And the right-hand side, this becomes less than 1 minus y over m. This is what we have. And this actually implies that all my xi's, x1, x2 to xn, are between these two numbers. Okay. So each of them is between these two numbers. And then we use i.i.d, right? i.i.d gets into play. That will give me the probability of x1 being between these two numbers raised to the power n. Okay, and what is that? x1 being uniform 0 to 1. And the uniform part makes things a lot easier. So this becomes equal to 1 minus yn minus y over n minus x over n raised to the power n. But again, this has a condition, right? In order for this to be held, this to be held, this to be held, we actually need to have x over n being positive and less than 1 minus y over n. This is less than 1. We need to have that. And again, asymptotics make things a lot easier. Like I said, x and y are predefined. Okay, given x and y, we just want to know whether this will hold if n is large enough. And actually, yes. So what will hold for this? So this actually holds if both x and y are positive when n is enough. You can see why. Okay, when x is positive, then this x over n greater than 0 will hold for sure. And when y is positive and when n is large enough, then 1 minus y over, so when y is positive, then 1 minus y over n less than 1 hold for sure. And then between x over n and 1 minus y minus y over n. So you know when n is large enough, the left side is going to 0, the right-hand side is going to 1. So that's why we can have the left-hand side less than the right-hand side happen for sure. So that's why asymptotics make things a lot easier. And here, the only condition we need is x positive, y positive. That's it. Okay, and then what's this CDF, right? We have this. Then this CDF is the distribution of what? This is the CDF of what distribution? Because if we can answer this question, then we know what is the joint asymptotic distribution of n times x1 and n times 1 minus x1. Okay, to answer, sorry, my bad, not done yet, sorry. So we are here, we haven't got the limit yet. Okay, so before we ask this question, now we let n go to infinity. I forgot about the last step. We let n go to infinity, and by that fact, right, it's 1 minus, in the denominator, x plus y, in the numerator, n, right, raised to power n. So we can actually show that this is converging to exponential to the negative x minus y. Okay, and then here comes my question. This is the CDF of what distribution? So we want to answer this question. And you see, this gives us some intuition that it's equal to the exponential to the negative x times exponential to the negative y, right? And here, x and y are both positive. So if you recall in our last lecture, we have this, right? So if you recall in our last lecture, we have this right here. Exponential, the probability of n times x n minus 1 less or equal than t, converging to exponential t. And we actually show that if we change the sign, we get the CDF of the exponential distribution. So here, we want to use the similar argument. We are interested in asking, does this, because we know this nx1 is converging to exponential 1. So is n times 1 minus xn. Then the question is, how about their joint distribution? By looking at this, we get some hint that we can actually factorize the CDF into two terms, one about x only, one about y only. So then we're interested in whether the joint distribution is regarding the joint distribution of two independent exponential one random variables. That's our guess, and we are going to verify it. Okay, now my guess is, so my guess is the joint distribution of two independent exponential one. That's my guess, and I'm going to verify it. Okay, so let me define y1, y2 to be independent exponential one. Okay, and I'm going to verify for y1, y2, and what will be their CDF, not exactly CDF, but using the greater one, greater than, what would that be? Okay, so then the probability that y1 is greater than x and y2 is greater than y, okay, can be written as, now I'm going to use the independence, can be written as the probability of y1 greater than x times the probability of y2 greater than y. Okay, and this would be based on the CDF function of exponential 1. It's actually 1 minus 1 minus exponential to the power negative x. That's this one. And the second term is 1 minus 1 minus exponential to the negative y. Okay, and then you can easily see that this is exactly exponential to negative x times exponential to negative y. So we verify that. And so the conclusion is that we can say n times the minimum and n times 1 minus the maximum. These two things are jointly converging to y1, y2, where y1 and y2 are independently drawn from independently following exponential one distribution. This is a very shocking result. The reason is that we know in the non-asymptotic sense, x1 and xn, one is the minimum, one is the maximum. They are not independent for sure, right? They're not independent because they are both based on the same sequence, x1 to xn. We sort the sequence and we take the minimum to be x1, the maximum to be xn. They are not independent for sure, but asymptotically, if we look at these two margins, okay, between the minimum and 0, between the maximum 1, these two margins behave like two independent exponential one random variables. If you scale them both by n, that's actually very interesting. Okay, but this is the result we actually derive from this, the CDF. Okay, so coming back to the original question about the range, Rn. So now you see Rn, we're just one step away. So you know that because the sum of two independent exponential random variables, we actually know what this distribution is. This is what we call the gamma distribution. So we can actually say it's the gamma 2, 1 distribution. So the 1 is the rate parameter. It has the same meaning as exponential. And this 2 can be considered as we have two things adding up. So this is a way to interpret the gamma distribution when this is an integer. That is, when the first parameter of gamma is an integer, you can interpret gamma as the sum of independent exponential random variables. Okay, and then we can have by the asymptotic joint asymptotic distribution n times the minimum plus n times the 1 minus maximum is converging in law to y1 plus y2, and that's following gamma distribution. So what we're applying here is the first statement of Slutsky's theorem, right? The continuous mapping theorem. So that's why we can apply this to the joint distribution, and then we can still have the convergence law. Okay, and what's the left-hand side? You can see this is essentially n times 1 minus the range, 1 minus Rn. That's exactly what we're interested in. So finally, we derived the asymptotic distribution for Rn as this. So 1 minus Rn, if you remember this figure, the thing I draw here. So 1 minus Rn is the sum of those two parts. And here for this, the sum, we multiply it by n. And then we show that this is convergent in law to gamma to 1. Okay, so that's all I want to say about the range. And the range is essentially depending on the joint distribution of the minimum and the maximum. Now let's continue our discussion about the uniform distribution by moving to example 4. Now we are interested in the joint asymptotic distribution between the maximum and the second maximum. Okay, so still the same setting. They are i.i.d. uniform, 0 to 1. And then we're interested in the joint asymptotic distribution of this. Okay, it's no longer the two boundaries, but the second maximum and the maximum. Okay, so one thing I want to say is that, so before we show it, okay, so one thing I want to tell you, it's a very, very interesting intuition. So it's again about that drawing. So from 0 to 1. Okay, now I'm going to have this as the minimum, this as the maximum, and this as the second maximum. So in short, the conclusion is that, so for these segments, let me call it 1, the length, this is called 2, and this is called 3. So what I want to say is that very interestingly, so if you think about these 3 segments, they are actually behaving like independently. So asymptotically, I should say. So what actually we can say is that, so asymptotically, so this n times the first segment is converging to, okay. So these 3 things are jointly converging in law to y1, y2, y3. And where these y1, y2, y3 are i.i.d. from exponential 1. This is a very interesting result, which means that the distance between 2 adjacent random variables from uniform 0, 1. So these things must be i.i.d. themselves. Then their adjacent distances are behaving like independent exponential one random variables asymptotically. So in our last example, we showed for this segment 1 and segment 3, but essentially we can talk about this for all those segments. So in this example, we are interested in the joint distribution of segment 2 and segment 3. So roughly, you know the idea behind here. So then you can see that if I want to talk about what's the asymptotic distribution of 1 minus xn minus 1, right? So by this argument, although we haven't shown yet here, but I'm just giving you the conclusion. By this argument here, it's equal to n times 2 plus 3. And this is, we know it should converge to the sum of 2 exponential 1. So we guess it should be gamma 2, 1. Okay, but this is our guess. Let's verify it. Okay, so we're going to verify this. So again, we are going to show what's the distribution of this. So we're interested in showing this joint distribution, and for the right tail, n times 1 minus xn minus 1, n times 1 minus xn. So it's a two-dimensional vector. We're interested in its probability being greater than xy, and want to derive that. Okay, so the reason we're not using the less or equal than is for the same reason I said. It's always to say that the maximum be less than something. So every x1 to xn is less than equal than something. That's easier to work with than saying the maximum being greater than something. So same argument. So then you see by just an algebra operation, this is equal to xn minus 1 less than 1 minus x over n, and xn maximum less than 1 minus y over n. Okay, so how do we derive this probability? We need to consider two cases. So first of all, if, you see, if 1 minus x over n is larger than 1 minus y over n. So in other words, the upper bound on the second maximum is larger than the bound on the maximum. Then the first bound is essentially meaningless, right? It doesn't provide us additional information. So when will this happen? This will happen when, you can easily see that, when x is less than y. So when x is less than y, then the first bound is not useful, right? So then this, let me call it star. So then star becomes equal to just the probability that the maximum is less than 1 minus y over n, because this is a tighter bound. And again, by the i.i.d of x1 to xn, it's equal to 1 minus I raised to the power m. And we know that this is converging to exponential negative y. That's the thing we're already familiar with. Okay, and then if this does not hold, instead, we do have 1 minus x over n less or equal than 1 minus y over n. Okay, when this happens, then essentially it's equivalent to x greater or equal than y. Okay, and and one more thing. For this to be held, we need to have x and y to be both positive, right? If it's not positive, then we will not have a formula here. Okay, so then I should say it's 0 less or equal than, yeah, when this happens, and this should be positive as well. So in that case, then the upper bound on the second maximum should still hold. Okay, should still be meaningful. So then what this actually means is that the second maximum is less than 1 over 1 minus x over m. That's the second maximum. It must be there. And the maximum must be between, right? The maximum must be between this and this. So sorry, I should say that, right, so the second maximum can be, yeah, that's right. The second maximum is lower, less or equal than that. And the maximum must be greater than the second maximum, but it's bounded between this, bounded above by 1 minus y over n. So essentially, what we can say is that we have n minus, okay, let me continue to write this down first. X minus 1, sorry, this is a typo. So what we can say is that out of our x1 to xn, okay, we have n minus 1 of x1 to xn less or equal than this. And we have 1 of x1 to xn to be between 1 minus x over n and 1 minus y over n. This is what we will need. Otherwise, we would not have the second maximum under this, but the maximum under that. So that's how the constraint will be like. Right? If everything is less or equal than 1 minus x over n, then we can just write xn less than 1 minus x over n, and it's not equivalent to this event. So when this event happens, it must be that we have n minus 1 of those less than 1 minus x over n, and the remaining one is between this and this. Okay, and in order to write this out, we need to use combinatorics. Okay, so, and sorry, my bad. This is actually one case. And another case is that everything is below 1 minus x over n, sorry. So another case is that I do have everything, the maximum, less than 1 minus x over n. Yeah, that's the second case. So they together define this. So basically I separated this event into two cases. One is that everything is under 1 minus x over n. The other case is that only n minus 1 of them is under 1 minus x over n. And the other one is between those two things. Okay, so then for the first probability, I need to use combinatorics. Okay, I have n of them, and I only need one to be in this interval. So it's an n choose one problem. So after I choose that one, for n minus 1 of them, their probability are under this, right? The probability that they are under this is actually 1 minus x over n raised to the power n minus 1. And for the remaining one, the one I picked, it's between this interval, and the length of this interval is actually, here I know x greater than y. So this is actually x over n minus y over n. That's the length of that last bit of interval. So this is the probability for the first part. And the second probability is easy. Everything is under this upper bound. So 1 minus x over n raised to the power n. Okay, so what's left? So the first term actually can be easy to simplify. This is n and can cancel with this n in the denominator. So the first term actually becomes, okay, 1 minus x over n to the power n minus 1. n times x minus y. That's the first term. Second term, 1 minus x, this. Okay, now I'm going to let n go to infinity and see what the limit is. Okay, letting n go to infinity, you know, this minus 1 can actually be ignored because n and n minus 1 is on the same order. By letting n go to infinity, the first term gives me exponential to the power negative x times x minus 1. And the second term is exponential to the negative x. Okay, so that's the limit for the second, for this case, when x is greater or equal than 1. So we are basically discussing those two cases. Then, finally, what's the limit, right? So what distribution has this shape? So it's CDF, it's joint CDF is either exponential to negative y or this. So let me simplify this a little bit by writing this as exponential to the negative x, 1 plus x minus 1. Okay, then what would be the distribution for that? So the question is, what distribution has CDF of this thing? So it's equal to exponential negative y. If we have this, or it's equal to exponential to the power negative x, 1 plus x minus 1. If, okay, we just want to find that distribution. And here is our guess, like I said. So my guess is, if we scroll back down, my guess is that for the first term, n times 1 minus x and n over 1 and minus 1. And my guess is that this is converging to gamma 2, 1. And this we know is already, we know this is converging to exponential 1. So that's my guess, right? So if I use this, I would actually guess that this first one is converging to y2 plus y3, while this is converging to y3. And let's verify whether my guess is right or wrong. So let me get a new piece of paper. So based on my guess, my guess is that it's actually the distribution of y1 plus y2 and y1. Okay, where y1, y2 are independent exponential one random variables. So let's verify that to see whether this distribution is indeed what we derive over here. So check. The probability of y1, basically we're going to write as y1 plus y2, y1 greater than xy. Okay, so what's that probability? Again, we can write it as y1 plus y2 greater than x and y1 greater than y. Because here x and y must be both positive. We know that since the y1, y2, they are exponential 1, they are positive. So again, we face the discussion about the relative order between x and y. Which one is bigger? Okay, so following our previous conversation here, if x is less than y, okay? If x is less than y, then the first constraint is not useful. It's implied by the second. So the star is equal to probability y1 just equal to y. Okay, and we know this is equal to 1 minus the CDF, 1 minus exponential exponential negative y. And we get exponential negative y. So exactly the same as what we have here. Okay, otherwise, if we have 0 less than y less or equal than x, so x is greater or equal than y, okay, then we need some discussion. So this means what? So the star, we need to keep both terms. So we need to derive the probability for that. And the only thing we knew is y1 and y2 are independent, but y1 plus y2 is not independent of y1. So we cannot factorize this probability. We have to deal with this. So if you have seen this in your undergraduate probability class, essentially, in this case, we're interested in doing integration over this area. Here, both x and y are positive, right? Both x and y are positive. So then what's this area? Let me call this y1 and this being y2. So this line, if I call this x, this line is essentially corresponding to x, y, this is corresponding to y1 plus y2 equals x, okay? So this line is y1 plus y2 equals x. And I also need to have y1 greater than y. So you see, and y here is less or equal than x. So if I call this y, if I call it y here, then essentially the area I'm interested in would be defined by the vertical line and this line, this horizontal line. Okay, so what it is, maybe I should draw this horizontal line a little lower. Okay, so the area I'm interested in would be this area. So it's defined by the vertical line and the diagonal line. So I'm going to do integration in that area based on the fact that y1 and y2 are independent. So you see, how should I do the integration? The first one is that I can, so to do the integration, I can do it in two ways. So one is that I can separate, because this area is actually a little complicated, right? So within this area, so it's not just defined by this line or this line, it's actually two lines. So one way to do this is that I can separate, so this part. So I can separate the area between y and x. So that is for my y1 between y and x. Okay, so for this area, you see, in this area, my y1 go from y to x, and my y2 go from this y1 plus y2 equals x line up to infinity. That's the first part. And the second part is that y1 equals y, right? And that's actually here. Let me see, y1 equals y. So yes, let me see if I'm right. So basically here, what I need is that, maybe I don't need to do the division, am I right? y1 plus y2 equals x is this line, that's right. Yeah, my bad, sorry. I think I made a mistake here. I forgot about the positive part, that's why. Sorry. This part should not be there. That's the negative part. So it's actually defined by this line, and this line. Yeah, that's what I want to say. Let me redraw the picture. Don't forget about this one. So what I want to say is, this is y1, this is y2, okay? And this is the line. The line shouldn't go down or up because we are restricted to this quadrant. This is the quadrant. This is the y, the positive part. So this is y1 plus y2 equals x. Okay, and that's x. And we also want to have y1 equals greater or equal than y. So that's y. So what the area I'm interested in is actually this part. Okay, it's this part. So it doesn't go down, but it's constrained by the vertical line and the diagonal line. So that's why I said that to make the integration easy, we separate it into two parts. One is this part. I call it part area 1. One is this part. So after x, that's area 2. So then you can see that by this separation, okay, for area 1, I'm basically going to let y1 go from y to x, okay? And for y1, its density, let me call it exponential to the negative t. Okay, so t represents y1. That goes from y to x. Or maybe I just call it not t, y1, lowercase y1. That's more intuitive. And for the y2, it actually goes from this diagonal line to positive infinity. The diagonal line is what? It's actually y1 plus y2 equals x. So it's basically x minus y1 to infinity, and its density is exponential negative y2. So I have dy1, dy2. Okay, that's the integration over this area. And for the second area, it's easy. It has nothing to do with y2, just y1. So that is equal to, second area is just the integration from x to positive infinity for exponential negative y1, dy1. So that's basically 1 minus the CDF of y1 at x. So therefore, doing this integration here and here, I can easily show that this first part of integration is equal to exponential to the negative x of x minus y. And the second part is exponential to the negative x. So you see, combining them, I'm here. This is equal to exponential to the negative x, 1 plus x minus y. And this is the case when y is less or equal than x. And it's exactly what I have here. So I basically verified that the limiting CDF I previously derived is just the CDF of y1 plus y2 and y1, where y1 and y2 are independent exponential 1. That's it. So in conclusion, we verified the guess I gave in the beginning, that is the joint asymptotic distribution of 1 minus x n minus 1, the second maximum, and n times 1 minus the maximum. These two things are converging in law to y1 plus y2 and y1, where y1, y2 are independent exponential 1 random variables. So in other words, this is the very interesting conclusion we reach about these order statistics, as I said. So if you think about, you have n independent independent random variables between 0 and 1, uniform 0 and 1, and you take the adjacent distance between your ordered statistic, and then what you found is that those distances are asymptotically independent. And if you multiply each distance by n, then each distance is asymptotically exponential 1. So that's a very interesting result. Okay, so last part we are going to show you before we finish today is a very important use of the uniform result. With the uniform result, we can get other result, the distribution, other distributions. So the first thing
I'm sorry, Professor. Sorry to interrupt. I just I'm wondering, does it automatically follow that all the intervals are exponential, or could we just use the same method to demonstrate that? Is there like an inductive argument that this shows that all the intervals are exponential and independent?
We didn't show that, but you
asymptotic?
can prove it using the same method as you said.
Okay.
Okay. You can just get, so there, how many intervals are there? There are m plus 1 intervals, right? There are m plus 1 intervals. So you can show that for any fixed number of them, right? But if you have m plus 1, then you have a trouble. Then the dimension is going to infinity. So that's why you have to pick some intervals to look at. If you pick 2, you pick 3, you pick 4, that's up to your choice. But once you do that, then you just use the same argument. You just do the, n times that interval length, and then you show what's its asymptotic distribution, what does it converge to, and the joint asymptotic distribution. And then you show, okay, that limit is basically the limit of the combination of independent exponential one. So the same technique.
Okay, thank you very much.
Okay, so the last bit is the use of that, right? So as I said, you may wonder why you are interested in uniform 0 to 1. So this is why. So why uniform 0 to 1 is interesting. So this is because of an important result. So let f be a continuous and invertible CDF function, okay? And let x follow, let u follow uniform 0 to 1, okay? So then what we can say is that this is a very important result. We apply the inverse of the CDF to u, and this transform random variable would follow f as its CDF. And this is the reason why uniform is so interesting, because we can use it to create a random variable that follows a continuous distribution. And let's verify that. So the proof is just one line. We basically need to show, okay, for this thing, the target transform random variable, for this to be less or equal than t. Then by the invertibility, we have u less or equal than ft. And this is by the monotonicity of the CDF, okay? And because u is uniform 0 to 1, then we immediately have this is equal to ft. And that proves it. Okay, this is how we say this. If this random variable, right, as a random variable, if its probability being less or equal than t is equal to ft, then yes, immediately f is its CDF. So with this important result, we come to example 5. So in example 5, we are interested in, so now our random variables are no longer uniform 0, 1, but they are i.i.d. exponential one random variables. And we're interested in the asymptotic joint distribution of xn minus 1 and xn. Okay, that's it. That's the thing we're interested in. Okay, so we want to basically apply what we know of uniform, and then we transform the uniform to be exponential one. That's the idea. So in order to do that, we need to derive what's f inverse. So here, the CDF of exponential, so CDF of exponential 1 is, we call this ft. We know it's 1 minus exponential to negative t. That's it. And what's its inverse? F inverse, it's called F inverse u, to be consistent with the notation here. Turns out to be negative log 1 minus u. Okay, so if we say u1, un, these are i.i.d uniform 0 to 1, then by this argument, we would have negative log 1 minus u1, negative log 1 minus un. They will be i.i.d exponential 1. Okay, the argument we just give. And then because we know the transformation, okay, this is also a monotone increasing function. The transformation does not change the order. So in other words, we can say that the second largest and the largest of u, after transformation, they become the second largest and largest of x. So in other words, we have this negative log 1 minus u n minus 1 and negative log 1 minus un. These things would have the same distribution. Here I just write equal in distribution. They follow the same distribution as x n minus 1 and xn. Okay, so that simplifies things quite a lot because here means have the same distribution. That simplifies things quite a lot because we already have the distribution, asymptotic distribution of un minus 1 and un, right? So that makes it a lot easier. So then what we have, if you recall, is n times 1 minus un minus 1, n times 1 minus un. So we are going to do that. And so what we have is this, right? So we know the distribution. We have the n 1 minus u n minus 1, n times 1 minus un. This is from our last example, converging in law to y1 plus y2, y1, where y1, y2 are i.i.d exponential 1. Right, that's what we had. Now we're going to go back to here. So this will tell me if I apply log to both sides, I can do it still by continuous mapping theorem. So I can have log n 1 minus u n minus 1. Negative log to be consistent with here. Negative log n 1 minus un. By continuous mapping theorem, CMT, this will give me negative log y1 plus y2, negative log y1. Okay, and this is equal to what? The left-hand side, we know this is equal in distribution to, by here, is equal in distribution to, here I have, because of the log property, log n can get out. So it's basically xn minus 1 minus log n. Here, xn minus log n. That's it, I'm done. So you see, I derived the joint asymptotic distribution for xn minus 1 and xn minus log n, and each of them is converging to the negative log of, this is the sum of exponential 1, this is exponential 1, and that's actually their joint distribution as well. So you see, this result basically confirms what we did in example 2. In example 2, we're talking about this alone. We say the maximum of exponential 1 minus log n is converging to Gumbo distribution. And here you see, this is another way to say what is a Gumbo distribution. So if you compare this to, if you recall example 2, what we have is that negative log y2 follows Gumbo. So you see, Gumbo distribution can be defined as, if you have an exponential 1 distribution, you take its log, and you take the negative, and then that will give you the Gumbo distribution. Okay, so that's all I want to say for the order statistics. We basically concluded extreme order statistics. That's all I want to say. And next time when we come back, we will start talking about sample quantiles. And the sample quantiles themselves have a very close relationship with the order statistics of uniform 1 random variables. Okay, so see you on Thursday.